Sorry. Hopefully everybody was writing your research ideas while we took that opportunity. So I want to thank John and company so much for inviting me to talk about this really very interesting topic that, as you'll see, is something we're running into more and more often. I want to recognize my co-authors on this. Amir Motlag is a postdoc, whose last week is this week. Ryan Jocelyn, who's a soon-to-be master's student, has been working on this for a while. And then at the bottom, Sam Levin and Bob Mackey. Sam, you're getting a lot of press today, who also were involved in this project. So I'm going to briefly, talk about what causes elevated temperatures in landfills, and then share a little bit of data that we've collected on how commonly this occurs at Florida landfills, and then run through a case study that you might find interesting. So this elevated temperature thing is happening more and more often, and as you see as I move through the slides, this is not the same thing as a fire. This is something that occurs deep inside landfills where there's no oxygen. So we'll look at why we think that is and what we're seeing in a few minutes. But I did want to point out that there's lots of press about, they call it landfill fires. It's not really a fire. It's, again, deep inside the landfill. It's causing nightmares. It's causing threats of nuclear waste. I think these are a little bit overblown, as you'll see, but there are serious implications about having these elevated temperatures if they're not controlled. So a few years back, we actually did a survey of landfill owners and operators about this. We didn't get a huge number of responses, but I thought they would be interesting, and you'll see that, there's all kinds of landfills responding, that these elevated temperatures are occurring in all kinds of different landfills, and not just, again, at the surface, but also deep inside the landfill under a variety of conditions. So we asked them if they had seen this, what they observed before the elevated temperatures occurred. And you can see a bunch of different things happen, but for the most part, there it is. It was hot loads, and then also strong winds, and then of course it could be dry, it could be wet, it could be, only a few of them said pulling too hard on their landfill gas extraction system, which was a surprise to us. And then there were a bunch of others. How did they know they had this condition? Well, for the most part, they're seeing smoke or steam. So again, this is close to the surface, and they're seeing evidence of it. But some other things, carbon monoxide a little bit, sudden depression, and some cracks in the cap. What did they do about that? Well, most of them excavated so they could get to the area of high temperatures. A few of them put water in, a lot of them covered with soil, and just a few did what we commonly think about, injected at great expense some kind of liquid nitrogen or something like that. It took them, in some cases, less than a day to control this, but in some cases as long as a year to extinguish these elevated temperatures. And again, what did they see? They saw surface collapse, they saw flames when they were excavating, they smelled things that they hadn't smelled before, and then some other things. So again, most of these obvious events, are near surface events. But as we'll see in a growing number of cases, these are deep within the landfill. And so we need to differentiate between fire, which we see flames, and there's almost always oxygen involved, and some of these other conditions that can occur, such as smoldering at relatively low temperatures, above the temperatures we're comfortable with, but no or low oxygen, versus ignition, where there's oxygen and there's flames and there's a rapid temperature transition. What we're beginning to think more and more frequently, we see what we call pyrolysis, which many of you may have heard of. It's something that occurs at under low or no oxygen conditions, And it typically requires a heat source, but we're beginning to see that there's conditions where we can have pyrolysis, which is destruction of chemicals, things breaking down and can release heat rather than need heat. So different things occurring deep inside the landfill under the high pressures that are occurring there. So what do you need to have one of these elevated temperature events? You need, first, an initiating reaction. So sometimes this is oxygen, particularly close to the surface of a landfill, but sometimes it's a reactive chemical deep inside the landfill that is sort of promoted by elevating temperatures from biological things, and then we have this initiating reaction, this catalyst, maybe you could call it. We're finding that we need moisture. So moisture is required for biological degradation, as we all know, but it's also involved in some chemical reactions, some abiotic or not living reactions. And we need high temperature. So combustion, which is a near surface reaction, is going to occur at very high temperatures, whereas pyrolysis is going to occur at lower temperatures, but still higher than microbial, the biology can survive at. So we said we need this initiating reaction. We need a source of heat. Often the heat is from biological degradation, aerobic or anaerobic, but this is not enough heat to make these elevated temperatures occur. So again, we think heat is coming from when chemicals are oxidized perhaps, or broken down into simpler molecules, that's pyrolysis. Heat can also be derived from, again, if you have oxygen near the surface, some absorption of oxygen, but more likely chemical reaction or the degradation of the fuel source, which is the organic materials in the solid waste. It can occur from hydrolysis of metals. Any of you have used calcium oxide and you add water to that lime, you get heat. So different reactions such as that can also contribute to the heat. Or just condensation of evaporated water, and this is what moves the high temperature through the landfill. The water evaporates, uses heat, and then when it condenses, it releases heat. So this is a really complicated situation. We all know that landfills are not simple entities. You know, there's lots of chemical, physical processes going on. So this elevated temperature is a bit complicated, and this is a really busy slide, but I created it because it helped me to understand what might be happening. Again, lots of people studying this, we don't know exactly what's happening. But if you look down here, we have anaerobic reactions. This is the normal thing in a landfill. This is what produces methane. And it does generate some heat. Whoop, John, your cooler's in the way. Where'd I go? Can't see this thing. Thank you. But we still can't see it. Oh, there it is. Okay, so we have the normal biological degradation, some heat produced, and a warm landfill. So slightly elevated temperatures, maybe even as high as 100, 120 degrees. And then we have aerobic biological degradation and maybe some low energy chemical oxidation. We're not really sure about that. But this is where you intentionally or unintentionally put air into a landfill. We're going to get this biological reaction. We're going to generate heat, and that's going to promote some slow pyrolysis, which also generates heat. So in that case, we've got a warmer landfill, but we don't really have these elevated temperatures that we'll be talking about. But that heat that's generated can promote some of these high energy chemical reactions, I'll talk about in a second. And these high energy reactions then generate heat and lead to the slow pyrolysis, which means things are breaking down and some heat. But again, maybe not so hot. But then we have the situation, and by itself, these high energy reactions can create these hot landfills that we're talking about. Or it can promote faster pyrolysis because this needs heat, and that produces some breakdown things, which I'll show you later, some byproducts, and if you get air with that, you got combustion. So this is a situation where things are breaking down, you expose the waste to the air, and boom, it's burning. So what we think is that these high energy chemical reactions are things like aluminum, iron even with sulfides, calcium oxide, calcium silicates, and other metals. So aluminum is the cause of the Rumpke, the Ohio landfill that was hot for so long because they took some aluminum dross waste. But these other things occur if you're putting ash in a landfill. You have that potential to occur if you've got water and organics in the perfect mix. So just to kind of summarize in a little simpler way, we have anaerobic reactions at 100 to 130. We have aerobic, maybe gets it up to 150. And then we have these abiotics. So this means it's not living because it's now above the temperature that these organisms can tolerate. And we have some pyrolysis, and then eventually we could get ignition, but ignition occurs at really high temperatures. So deep in a landfill, we're not getting ignition. It requires oxygen, it requires exposure. So just to kind of summarize how one of my students put this together. So we've got what people called landfill fires, spontaneous combustion, these things near the surface and visible with flames, but then we've got these deep elevated temperatures. It's not necessarily super high, but it's still above the magic 131 degrees. And this is just a fire at a landfill in India that was visible from a satellite. So you have these very visible things, but this is very different. And it can impact a liner. It can impact gas collection. Anything inside the landfill. It's certainly going to prevent methane if it gets high enough from being produced, and could create some settlement if you truly get degradation of waste. So we've been looking at data. We've been using Oculus, and some of you have sent us some data. And what we did was we looked at all these data, thousands of data points, and we looked at the percent of, and we're looking at gas well data, which may be a little bit lower than what it is actually inside the landfill, but that's what we have. We have gas well data that was over 131 degrees Fahrenheit, the magic number. And then we also looked at how many of those landfills had that certain percentage. So we can see that 100% of the landfills we looked at had less than a third of their wells. I should say that. So none of the landfills that we looked at had more than about a third of their wells with high temperature, but that's a pretty high number. And then we had about a third of them that had no well data that was above 131. But then we have a third of them that are around 10% or greater. So a third of these landfills that we looked at had 10% or greater of the well data more than 131 degrees. So, I was a little bit surprised to see that it happens as commonly as it does. So just a case study, I'm not naming any names. This is one of the landfills that had, I think, 10% of the wells were elevated. So they asked us to look at their data, so we looked at a bunch of their wells, I think 13 wells, some of which were high temperatures and some of which weren't. The elevated temperatures are kind of in this area, the west side of the cell. We excavated 2 wells to look at the waste itself and measure deeper into the landfill. So I'll show you some of that information. And then also looked at some wells that were not elevated, just as a kind of a comparison. So this is where we did this drilling, and we saw poor Bob Mackey ran and stuck an infrared to measure the temperature as soon as we brought it up. And so they call this the beer belly distribution of temperatures. There's all different shapes, but this is very common where near the landfill surface it was warm. I was sitting on the surface and it was warming me up there. but but not nearly as warm as it is in this middle section. And then it cools off. We did some measurements in the leachate collection system and found that there didn't seem to be any transfer of heat down here, so we're fairly confident that the liner system is unimpacted. But we did pull up some wood that looked a little bit charred and saw some higher temperatures. So in this area of the landfill, they did take some material called Enviro, which is a mixture of biosolids and ash, so coal ash, as liner, as daily cover. Sorry, so we feel like we've done some other studies I'll share that's that initiating reaction. So that's what the biology got it up so far, and then stuff in the ash got it up further, and there's we'll see. So it's fairly moist in that area. These are the two wells that we looked at. So we measured moisture content of the samples we pulled out. So drier at the top and bottom. For one well, pretty wet in the entire one. You're looking at around 40% moisture content. It's pretty warm. Volatile solids were much higher in that region than they were above and below. And so our feeling is that with these higher temperatures, there's not a lot of degradation going. So it's not like we got a fire and it's consuming material. It's just the opposite, in fact. We have high temperatures and it's impeding degradation because the microorganisms are either inhibited or not able to function. We looked at something called biochemical methane potential, which is a measure of how much stuff you have left to produce methane. So in that center area, we had pretty high compared to low here, BMPs, which suggests, again, not a lot of degradation is going on. Again, no combustion eating up the waste or anything like that, but on the other hand, not a lot of degradation, so not optimal. We took some of that biosolids ash mixture and we did some tests on it, and we found that there was a lot of calcium, just looking at the inorganics, iron, silicates, and aluminum. And so, these came from the coal ash and are likely involved in these exothermic reactions, these energy-producing reactions, and perhaps not occurring until the temperatures got up enough to initiate these reactions. but this produces heat, leads to pyrolysis. Pyrolysis maintains and propagates this heat inside the landfill. So just to show you some data, we're going to look at a non-elevated temperature gas well. Here's the 131, and you can see that there were a couple months it was above 131, but in general it's kind of following a yearly pattern, and it's well below 131 degrees. The other thing that we looked at was the ratio of methane to CO2. And so, we want this to be above 1, because that means the methanogens, the methane producers, are healthy and happy, and they're producing lots of methane. Sorry, it should just say methane to CO2. So this is well above 1, with just, a couple points maybe associated with higher temperatures, but a pretty healthy looking data set. We then looked at an elevated temperature gas well. Again, we're measuring gas temperatures, not waste, but it's a good indicator. And here's the 131. So you can see, with the exception of a couple points, we have pretty warm conditions, not the hottest that's ever been recorded in elevated temperature landfills, but fairly warm. I'm not sure what happened here. It was a good thing, but then they decided to stop extracting gas. And this is a common reaction to elevated temperatures, the theory being we're pulling in oxygen, and so let's stop extracting gas. And in truth, that's the opposite of what you want to do, because these situations are too deep. The gas data supports this. It's not oxygen. So if you stop pulling on your gas wells, what you're doing is you're trapping the heat in there. So moving the gas, moving water, moving anything through that area, extracts gas. So, so we suggested that they turn the gas wells back on, and so, again, still elevated temperatures, but some indication that maybe it's finally, after many, many years, starting to cool off. Looked at, again, the methane to CO2. Sorry, that's not correct, but, and here's that one. So you can see, interesting enough, we still have methane. So we're still producing methane in this area, but not enough to make that methane to CO2 above 1, which indicates, you know, a healthy area. So significantly below 1, in some cases quite below out here. So again, the methane to CO2 tells us that things aren't great, but we're still producing methane. And so there are certainly laboratory experiments that show that methane production can occur at pretty warm conditions, so 55, 60, 130, 140 degrees. You can still get some methane production, probably at a slower rate, but they can still tolerate it. Just wanted to show you, some temperature contour maps that from about 10 years ago, when the temperatures first started going up. It's hard to see the pointer on this. So you see on that west side where that enviro is placed, high temperatures, and they just progress over time until it's pretty much covering the entire area that I just showed you. And now more recently, that high temperature is starting to maybe collapse and seeing cooler around the edges there. This is some very recent data that we just went monthly since they opened up gas extractions. Not too interesting, not a lot of changes this year, but again, compared to initially, you could see the changes. So this is the methane to CO2 ratio. The pinker it is, the lower that methane is. So you can see that pink area, the purple area is growing with time as the temperatures increase. But still, it's hard to see what this is, but it's, you know, still methane is being produced, and interesting enough, even at the higher temperatures. So we also looked at the leachate and compared some of the aromatics and ketones. We picked these because, first of all, the other parameters weren't changing, so there was no difference between, you know, ammonia wasn't changing, COD, but these materials dramatically changed. It's statistically significant, although it's not that high concentrations, but there's a definite difference. And these kind of chemicals are some of these things that I mentioned in pyrolysis. When you start decomposing the waste, these are some of the things that are produced. So this also supports that we have this pyrolysis stuff going on. So just about done. So our conclusions for this case study is that you know, elevated temperature, it's a rare event, but and not completely understood event, but seems to be increasing in number, but it does happen without fire. In our case study example, high temperature doesn't seem to be impacting the liner system, which was good news. That's not always the case, but in this case it was. We really think that this is pyrolysis, that this is slow pyrolysis that produces heat, moves the heat through the landfill, even in areas where there's not necessarily any of this catalyst stuff. We did an elemental analysis of this material and saw some things that could be exothermic energy yielding material, such as hydration and carbonation. We really feel that air intrusion is not causing these high temperatures, and I passed through the slide without pointing it out, but the gas temperatures, we can compare how much nitrogen is in there to how much CO2 is being produced, which would be produced in the air. Anyway, this ratio is outside the range that we would expect if we had significant air intrusion. There might be a little bit, it might be contributing to a minor extent because we do see some nitrogen, but not very much. And we truly feel in this depth that there's no air intrusion occurring. And we also feel, fortunately, that there's not a significant amount of waste degradation, which would lead to too much settlement and unstable conditions in this case study. So I want to acknowledge Hinkley, of course. And I meant to say at the beginning of this that I've had almost 80 graduate students over my career, and I would say somewhere around a third to a half have been supported by Hinkley. So it's made a huge difference in I think the solid waste field. And they're all over the country, all over the world actually. So the word is spreading about Hinkley. And of course, S2LI, our partners in the case study, thank you so much for all your help, Sam. And Bob. Is Bob here? No, he's not here. Oh, yeah. Okay, well, thank you. I hope I didn't show too many chemical equations, but I'm available for questions, I think. Jason? Yes, Sam.
2 questions.
Okay.
Didn't Anne Germain tell you about a similar Enviro site?
She did. Delaware had similar, yes. High temperatures, they used it for cover, yes.
And second, could the presence of methane be the result of the belly, where you're getting methane above the belly and methane below the belly?
It could be, yeah, it could be drawing from areas, you know, we don't know exactly where gas comes from with any gas well, but actually I think it is possible that even in some of the higher temperature areas we could still be producing methane. But you're right, it could be coming from the cooler regions that we saw, particularly now that we have more cooler regions on that side. Thank you for not asking a hard question. Any other questions? Yes, Jason.
Dr. Reinhart, in one of your first slides, you showed conditions at time of observation of the elevated temperatures, you know, some physical and environmental conditions. Did they also look at sites that only had maybe intermediate soil cover versus sites that had a full encapsulated final closure?
Yeah.
And maybe like high winds really wouldn't be impacting a site that was completely cut, you know?
I think that he was just asking, did we connect some of these high temperatures with the cover system, or, you know, if there was an impermeable cover, high winds wouldn't occur. So I think the moral of that story, and that had nothing to do with the case study, is that these things happen under all different kinds of conditions. They're really hard to predict. And there's a major effort going on between North Carolina State and University of Virginia that's supported by the Environmental Research and Education Foundation. I mean, they're putting nearly $1 million into this study, and this is all coming from private waste companies who are very concerned about this because they want to predict, they want to, you know, let's not do what causes this and just stop it before it starts and not have to worry about it. I mean, you see these elevated temperatures for 10 years, so this is, you know, not easy to stop deep in the landfill. So they really are working on a model. A lot of my information came because I'm on a stakeholder group looking at what they're doing. So yeah, it could be, some of them, yes, had intermediate cover. Some of them had final cover. It's all of the above. But most of the data that I showed in that survey, I think were more the close to surface kinds of things, and not the deep landfill, not fires, elevated temperatures. Anything else? Oh.
Is there an average age of waste that this occurs to, or can this occur at any stage in the life of the landfill?
Yeah, I think if you have, you know, moisture, you have stuff that initiates it, and you have organic material, it can occur and would probably likely occur somewhat shortly after the waste is placed, but the pressures also have something to do with it. Again, this is, I mean, I was hoping that I could simulate this in the lab, but without being able to generate the pressure of, you know, 30, 40, 50 feet of waste over it, I don't think we can really simulate that. But they are doing that with this North Carolina study. So if it takes pressure, then that would take a while. So if pressure is involved, but you still need a catalyst. Pressure and not pulling or pulling on, if you don't have that catalyst in there, and we don't, even though we put aluminum in there, it's not enough to initiate these temperatures. I feel very certain of that. So anyway, they're looking at the perfect combination of, and age of waste is one of those. Thank you, good question. Okay, well, thank you so much.